CLion, a cross-platform IDE for C and C++. Download now.
So my name's Kevin Carpenter, and today we're going to talk about mastering the unordered map. It's kind of fun to give a new talk and a little nerve-wracking too, but I hope that you learn a lot today and there's lots of questions. I did post inside Discord the link for the code, but I'll have a QR code at the end of all of this that you can scan as well. So let's get to it here. Okay, so for decades, at least for me, whenever I was taught C++ or learned, actually with my position or my age, I started with C++, which we all know. But I learned std vector first. And if you know from 2024, I love vector, almost always vector. It was one of my favorite talks to give. Who doesn't love growing an array and not having to do all that stuff manually? But if I wasn't using std vector, which to me is king, then it was std map, right? Key value pair. That's what we would be doing. And so std map, but std map is no longer the queen to std vector. That's just not the way to look at it, I don't think. And we're going to talk about why. And so if std vector is our default sequence container, and yeah, it's kind of a given, but I want you to think for a moment of what you go to when you're writing code as your default associative container. Do you default to std map? That's what I always used to do. Well, I'm telling you, std unordered map is the number 2 container in modern C++. And that's what we're going to talk about today, right? And so we're going to talk about why it's the dominant one. And so we'll look at some data and we'll do some comparisons so we can see how it actually performs. And the example code that I have, we're going to, of course, have slide snippets, but all of the example code works and will give you the same results that you're going to see in the slides. And we're going to go into the internals about how it works. And I think that is one thing that's important with unordered map. You really need to understand a few things. Otherwise, it is definitely the container that you can do wrong accidentally without realizing it. And then we're going to talk about when it fails and what those pitfalls are, right? And that kind of leans back to, how we make sure, knowing how it works, that we don't have it fail and we get the performance out of it that we're hoping to. So for this next 40 minutes or so, we'll end up going over the showdown. So we'll take a look at the performance of map versus unordered map, and I'll get to show you why you want to go to unordered map first as your default. Then we're going to look under the hood. So we'll look at how hash table really works, so you can better understand what's going on there. Then we're going to talk about the pitfalls. And these are ones that, I've definitely been hit with myself, and hence part of the reason for wanting to do the talk. So we'll look at hashing, we'll talk about collisions, and then we'll also look at what rehashing is and why it happens. And then we're going to look beyond. So C++ 23 flat map, and a couple other talks I've had people call this out, and I honestly hadn't used it that much. And so part of my thing for doing this talk, it was a great opportunity to look at it. And flat map is pretty incredible for depending upon your use case, and I think that's everything with C++. If you know the right tool to use, that's where we get our performance from. And then with the, unordered map or set, heterogeneous lookup has also been a big gain. And especially for what I do with work, which is processing credit cards, heterogeneous lookup has been a big add for us. And then in the end, I'm going to give you a new decision tree to help you understand, when you're getting ready to write some code, you'll be able to use this tree to know which particular container you want to pick. All right. So round one, map versus unordered map. Here we go. So std map, if you don't know, it's based on the red-black tree, and I am not a red-black tree professional by any means. I understand them. It gets us, a guaranteed O log n for lookup, insert, and delete. The keys are always sorted, and when I think about when I first learned to use std map, that was part of my thing, right? It's like, oh, well, my data's always sorted. Why wouldn't I want that? And it is, but that may not be the thing that you need, right? And so it's node based, which means it's pointer chasing. And because of that, it's cache unfriendly. The pointer chasing gives us part of that guaranteed O log n, and it makes the trees, very easy to use and be consistent on. But again, we lose the cache friendliness. And then stable iterators and references across all operations. I mean, that can be really important depending upon what you need, because that is something you have to watch with an unordered map. I will say that if you want to learn about red-black trees, Michael Samble has some really good short YouTube videos that he's like red-black trees in 4 and such. And he goes into talking about how rotate happens and such so that trees get rebalanced. And so if you want to know more, I definitely recommend his videos. They were great little bite-sized pieces. So stood map is what we learned, right? It works, it's predictable. But one of the things you have to keep in mind is log n, when you're at scale, that will add up. And so that's one of the things that we're going to, dig more into as we do this comparison here. So stood unordered map is a hash table. And on average, it's O1 for lookup, insert, and delete. Keys are unordered. And it's bucket based. And so when the data gets put into a bucket, inside each bucket, it is separate chaining. So it is linked lists. And, this is what we would end up calling a collision. And we'll get into that more later. And as the last one here points out, the word average here is doing heavy lifting, right? So it is O1 average, but that also means to make sure you're doing everything right. Because if you hit one of the pitfalls, then everything can go sideways pretty easily. All right, so we're going to look at our first benchmark here. So a little bit about what I do. So like I said, I work in the credit card industry and we process credit card transactions for a living. And I'm in the portion that they call an acquirer. So my customers are actually that terminal that you tap your credit card to, or, if you're on a web page, that transaction gets sent to servers that I handle. And then we reach out to MasterCard, Visa, Discover, whoever, get the transaction approved, declined, and pass that transaction back. And so all of the samples that I have are kind of flavored that way because it just happens to be what I do for a living. That said, they are, they are a bit slideware, but it is real in the sense that this is the type of technology and programming that I do from a day-to-day basis. So for this benchmark, you'll notice that it's source O2. So there is an O1 that is actually a bit more detailed, but this just worked better for fitting on the slide. So it's simple as possible. We got 1 million iterations that we're going to do, and we have a map and we have a hash. And so we are basically creating our key, which is that TXN plus an integer on it. And then we're assigning it an unsigned, UN32 value. So kind of funny thing, if you don't know, when you send in a credit card transaction, we never receive real numbers. So your, what is it? $8.50 latte is actually 8,500 pennies. And that's how we work with all of it. So if you look here, we're basically going to turn around and go through and do a lookup of all n keys. And in this first one here, we're looking at it with ordered. What isn't shown is that we run the same structure with unordered next. All right. And so the results of that is here. So even at 1,000 authorizations, we're looking at 50 nanoseconds in a stood map versus 18 nanoseconds in an unordered map. I mean, in the unordered map, that's a 2.9 time speed up just right off the bat. And if you follow it down the line here, you can see when you start hitting 10 million transactions or more, your speed gains just become huge. I mean, 8 times when you're looking at the 10 million transaction range in comparison. And so map climbs with n, right? And so if we look at the map, as we grow in the size of our container, it's climbing, whereas stood unordered map is staying in our O1 area. So at 10 million auths, we're looking at almost 9 times slower. And as an acquirer, where all I do is pass transactions all day long, milliseconds count when you're doing, 10,000 transactions per second. And that matters. Another thing that's kind of interesting about transactions for us for authentication, or not authentication, for authorizations, is that they, normally if you tap your debit or credit card, we're back to you in less than a second. But the standard for the credit card companies still let us go all the way out to 27 seconds. And the reason that is because, at least here in the States, you have small towns where the credit card terminals might still be on a dial-up. And with that being in mind, you have to have that extra time for the transaction to go out and back. And so the time to live on some of these also factors into when we're writing code. And so keeping things in the unordered map gives us that consistency, even as that map might be building in size or diminishing as we get the results sent back to a merchant. So at 10 million items, map lookup is 9 times slower. 10,000 transactions per second, milliseconds can become, SLA breaches. That's really the point. And so, why doesn't everyone just use unordered map? I mean, that alone should be your reason to move, right? And so, well, we'll see. All right, so under the hood, how does a stood unordered map actually work? And so a stood unordered map, there's kind of a pipeline, and it's got 3 steps into it. And so the first step is the key, right? So you take your key, you're going to run it through stood hash, and it's going to give back a size t, which is basically just going to be a very large integer number. From there, we're going to turn around and run a modulo on it based on the amount of buckets that the hash has, and that'll give us a bucket index, okay? And then from that bucket index, we can then go to that particular bucket and then do a linear scan to find the data. So let's look here more at step 1. So here we have a mid, and a mid is short for merchant ID. And this is, contrived, but this is actually what we work with. We end up getting a merchant ID that we always end up having to look up. So we store a lot of data based on this. And we'll end up hashing that mid, and then we're going to put it into a bucket. And so as you can see, if we take that first mid, 100001, it comes out to be that particular hash, which when moduloed ends up being in bucket 3. And then you can see, the same thing again. If we do it with another merchant ID, we end up being in the next bucket. So as I was saying, a mid, just a little bit more in the world of credit cards, merchant ID, these are contrived. I promise you, Amazon Web Services really is not mid 100001. It's actually quite larger. But the merchant ID is a unique ID that we use to look up things. And so this is something that we end up doing a lot of. And because we have so many of them, if you talk about having 500,000 or more merchants, and that doesn't count the amount of little terminals that they have on, each place, such as a grocery store, this becomes a massive list, which is why we use unordered maps a lot. So step 2 is put the bucket array. And so one thing about unordered map is it has some really interesting other methods on it, such as size and your bucket count, your load factor. So as you're working with an unordered map, you can actually get some details into how it's working. And so you can see how I do that in the under the hood example that's in the source code. But in this case, what I want to look at is the fact of, you can kind of see, our bucket 0 doesn't have anything. Our bucket 1 has our first mid in it. But the one I want to point out is bucket 3, right? Because bucket 3 actually has 2 items in it. And this is where we talk about that linear search part, because this is actually what is the start of a collision. And this is one of the items that we want to avoid. In a small example, it's not a big thing, but you get extreme examples. And as we'll see down a few slides here, that can really affect your performance. And so the thing that it comes down to is, even though we have different mids with the same modulo, it's like the amount of possible keys is really kind of unlimited, right? And so, that leads to kind of that pigeonhole principle, and multiple keys will eventually hash to the same bucket. And so the separate chaining is essential, but we do want to do what we can to help avoid that, because that's part of where we help make sure that we can keep our performance when working with an unordered map. So looking at the separate chaining a little bit more, so bucket 3 here again is the example. So if ahead of a linked list, right? And so our first data item is that first mid. The second data item ends up being our second mid, and each bucket is the head of a linked list. And so when two keys hash to the same bucket, that's how they get chained. And this is what occurs when keys collide. They end up being chained together. And so we'll look more at what ends up happening with that here. So the O1 assumes that each bucket has only one item in it, okay? And that's kind of key here. That's why I'm kind of talking about the fact that it turns into a linked list, because ON happens when everything drops into one bucket, or one bucket has all the items. So part of the buckets being set up is what we call the load factor. And the standard tries to keep buckets short by rehashing when the table gets too full. But, rehashing has costs. And so, the load factor is the size divided by the current bucket count. And when the load factor gets beyond the max load factor, well, that's when we do a rehash. And a rehash is going to allocate a whole new bucket array, rehash every element, and then reinsert all of them. And this too ends up being a performance problem if we're not careful. So this is when O1 becomes ON, or oh no, 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 as the title of the talk suggested. So I had to use the pitfall graphic because we're talking about pitfalls, but I have to kind of laugh at myself because, being the age that I am, this actually, I remember the graphics being a lot better than this, at least they were in my mind as a kid. And just to say, this is actually from the remake. So the graphics that are shown are probably even better than what the original was, but still it was a great game. So our first pitfall that we have to watch for is the bad hash. And we'll look at how that ends up happening. Our next pitfall after that is, of course, the collision. And collisions, as we were looking at, if you end up starting to get everything dropping into one bucket, then you basically start getting into, a far worse performance because you're using just a linked list and you're more linear now. And then finally, you have the hidden rehash, right? When you end up going beyond the size of your unordered map and everything has to be recalculated and regenerated basically for the unordered map. So we'll start with the bad hash. So you need to hash a custom struct. What could possibly go wrong with that? So following along my credit card theme, this is a transaction struct, or at least a very basic example of one. And so, we have 4 fields and we need to use this within our hash, and we'll use this transaction struct through the next few examples. So just, kind of take a look at it. We have a merchant ID. We have a card bin, and I'll talk about those in a little bit later. The card bin, if you don't know what that is, that's the first 6 to 8 digits on your debit or credit card. And that's actually how we learn to route where something goes. Like we can tell if it's a MasterCard or a Visa, whether or not you get rewards or not based upon that bin. Of course, we have the amount, which is, again, our pennies. And then in this case, we have a currency. And so we have our equality operator there that's just, being used for the struct so that we can turn around. And if we are doing that linear search through the data, make sure that we are actually returning the right one. So a good hash versus a bad hash. So the left side only hashes the currency, right? So we've overloaded the operator to generate our hash, but the only thing we're going to hash on is the currency. Now, this is obviously contrived. I mean, only hashing the currency for where I'm at, that's US dollars. So 99% of our stuff is going to drop into one bucket, and that's just going to be a collision. And so the thing I guess I would say, and I'll mention it a couple times, like when you know what your data, when you aren't sure what your data is, that's when I think it's easier to create a bad hash, right? Because you might think that the data that you're hashing on has, a wide range of values, but then once you write the code and you start actually processing that data, you find that perhaps it is not as unique as you think it is. And so then if we look over on the right-hand side, that's where we have a good hash, right? Because not only are we hashing each one of the IDs, but we're actually using a seed to go with it. And by doing that, we're making sure that, we have a good hash that's going to return a unique identifier, which is then going to help us make sure that our data is spread across the buckets more evenly. So things to think about. So the more fields we use, there is a cost, right? Because the more fields that we're using in our hash is more computation per lookup. So if one field you do have is that unique, then just use that one. But that's the part where I was saying as well, when you're working with your data, make sure you know what the data coming is. Make sure you know that you're going to have that uniqueness. Otherwise, use more fields. But just to say, you don't want to use every field, because if there's a cost, not if there is a cost, there is a cost to doing hashing. So your hash must match your operator equals, your equality operator. And so only hash fields that define identity. That's for certain. And mutability. Make sure you're not hashing a field that's going to change after insertion. Otherwise, fine will look in the wrong bucket. And I will say that one bit me once, and that was a lot harder for me to find the first time that I was creating my own hash. You step through it and you find it, but I think I probably went in circles for an hour or so the first time I ran into that. All right, so let's look at some more code here. So this is a boost style hash combine. And the thing that I liked about this one is it actually uses the golden ratio, which Knut put into use really well. And so what we're doing here is with the golden ratio and passing it to a left and a right shift. So we're not just hashing the value that's going to be the type that's going to be passed in. We're going to add the golden ratio. Then we're going to, with the seed, we are going to shift it left. We're going to shift it right. And it's going to give us a widely scattered output, far better than, even just a seed by itself. And you'll notice that, we're using XOR there when we do this, because without the XOR, it would just be commutative. And then next we have this fold expression. And the thing with the fold expression is it lets us make this apply. As you can see down in the struct below, we can just turn around and make this work for however many items that we want to pass into it. And so with the transaction hash there that we have on the bottom, we hash our values: merchant ID, card bin, amount, and cents. And so this is a good way to generate your hashes. Works in C++ 17, which, to me is interesting because, as much as we're now at C++ 26, for our production code, we're still just working into features for C++ 20, which, can kind of be a little disappointing when we start looking at flat maps like we'll cover a little bit later. But it also, this is just to give you a good example of something that'll give you a solid hash that makes it easy to use. And so when you call your unordered map, this transaction hash struct just gets passed in as your third parameter. And so that is how we're building our auth cache in this example. So we'll look at the next pitfall, which is going to be the collision catastrophe. And, this kind of follows along with the fact of where we were just talking about creating a good hash, right? By creating a good hash, the goal is to avoid this particular pitfall. And so what happens when every key hashes to the same bucket? And so, we'll start with this struct here, which we will call terrible authorization hash, right? Which, obviously we're not going to have one just return 42. The 42 is, of course, slideware, a little bit better or a little bit worse than our USD when it's 99%. But the point of this is to be able to show the performance differences, right? And so we're going to take a stood map. We're going to take the unordered map with a good hash and the unordered map with a bad hash, so we can show the kind of performance difference that happens when you don't get it right. You get too many collisions. And again, when you're writing your code, if you know the data that's coming in, this is probably pretty easy to avoid, or if you just plan it carefully. But it is one of those mistakes that is easily made if you're not careful, or if you just don't know that this is something that you actually have to consider when using unordered map. So here's the results of the pitfall collision catastrophe example. And so at 100 auths, compared to std map, you're almost 200 times difference. And by the time we get down, it just gets worse and worse. When you compare it to the unordered, the performance of the unordered on a good hash still beats std map, of course. But if you have a bad hash, which is then going to cause you to have collisions, your performance is just going to degrade terribly and rapidly. And so, your ON basically becomes, you basically have an ON linked list traversal versus O log N for a tree traversal of std map. And so I can't, stress enough that you really want to make sure that your hash is well set up, because by doing so, that's going to help make sure that you don't end up having collisions, which, will just set you up for a different level of failure. So with a bad hash, unordered map degrades to ON, which is worse than our regular map's O log N. And your fast map is now 100 times slower than your slow map, right? And so make a good hash. So the hidden rehash, what happens when the table gets too full? I'm guessing a lot of you use vector, and so I'm curious how many set their size on vector. Just do the clap or a thumbs up if you set your size on vector 80% of the time when you use it by default. Do you? Okay, okay, there we go. All right. So I think you can see where this is going, and that's kind of my point, right? Because what happens when the table gets full? Well, you have to stop everything. Every element has to be rehashed and then reinserted. And so I'm using an example here where we're talking only about 150 transactions a second over 60 minutes. But the reason I did this one this way is because, like I said, when we're doing authorizations, not every authorization just gets done within a couple milliseconds or less. We have some that'll hang on. And so as our table grows, as our unordered map grows, this is something that I actually have to watch for. And so we try to consider how much traffic is going to come into one particular node or another, and that helps us define how we're going to handle our maps. Because basically, as you can see, the time grows every time that we have to do a rehash. And so when it comes down to it, when we don't do reserve, our average insert time ends up almost being double as what it is if we do reserve. And our max insert time ends up being just massively worse, not to mention the amount of rehash events that we end up having. So when you're working with std unordered map, you might turn around and in your first bit of working it, if you start to see that performance problem, that would be my first thing to say, is you definitely want to turn around and look at using reserve if you aren't already, because it may just be that if you reserve the amount of space that you need to begin with, just like with a std vector, you're going to get that performance gain just because you're not having that rehash. And one thing I didn't do here, but it kind of made me think about too, is, this was just an example with that transaction hash, but it does make me wonder if the rehash is worse depending upon how many fields that you do have in your hash. And I would imagine that it plays a part, but I don't think it's as meaningful as just using reserve versus not. So 538 times improvement versus that worst case, just by making sure you use reserve. All right, so let's look a little bit beyond unordered map. This was a fun part for me to play with, because like I said, we aren't using C++ 23 yet, but std flat map, it's a sorted container backed by contiguous memory. It gives you like std map semantics and your std vector cache performance, which is just beautiful. But that said, it's, so basically if you haven't used std map before, it's backed by two sorted std vectors. So you have contiguous memory. With std vectors, of course, we have cache friendliness. So it's really super duper fast. But there's the trade-off. Inserts are more expensive. But one of the things that we use this for is bin tables. And so bin tables, like I said, that's the first 6 to 8 digits of your credit card. And depending upon what that is, it gets routed to different areas. Now, with the way bins are designed, there's currently over 100 million bins that are available. Fortunately, we only have to work with about 300,000 to a million at a time that are actually active. But still, for me to load up a bin table with 500,000 bins into a flat map compared to my unordered map, I'm looking forward to when I can move up to a C++ 23 compiler just for this fact, because these are things that we do in other methods that I think std flat map, well, I know std flat map would be much more efficient for. And so, yeah, just think of it as std map meets std vector. And if you have C++ 23, this was the easy gain to me was std flat map. And it was funny because I remember in my talk on Almost Always Vector, someone called me out and said, "Hey, did you use std flat map?" And when I gave that talk, I had not. And now I understand exactly why they had the look of shock on their face that I hadn't, because yeah, if you have 23, std flat map is the way to go. That is for certain. And so as an example of the performance, a std flat map with 500,000 entries, the iteration time is 2.75 milliseconds compared to an unordered map. I mean, just look at that. That's 7 times faster than an unordered map. And for that matter, your std flat map is, of course, faster than even std map. Of course, every container or structure that we use has its benefits, and you have to weigh the benefits of each, because again, std flat map, the insertions are more expensive than say with a std map, but your read times are just incredibly fast. So heterogeneous lookup, this was a great one that we had added for C++ 20 with unordered maps. Or unordered sets too, because basically it lets us search for elements using a different key type. And so we're going to go over this in a couple slides, because this first slide here, we're looking at the setup. So you have to have both a hasher and a quality. And the thing that makes this work for heterogeneous lookup is the using is transparent there. So you have to define that within each. And in this case, what we're doing is we're going to use a string view. And part of the reason we're using string view is because before doing it this way, it would end up making a copy, right? Because we would have to end up copying over to a temporary to be able to do our comparison. And so I'll go a little bit more into why we end up liking string view, but if you ever are interested, there is a standard that is ISO 8583, and you can Google this. This is actually the standard that defines how credit card data is formatted, like in a transaction, how it has to be sent. And it actually uses bitmaps with defined fields. And so for that, string view ends up being incredibly efficient. And so this is why this was such a big win for us, is because now we didn't have to do our copies, and we were able to basically do our comparisons with a straight string view. And so to use this, you're basically going to initialize your unordered map with, 2 extra parameters, your string hash and your string equal as your 3rd and 4th parameter. And then when using it now, the traditional way we would have had to do it is that first line there, where we would take the iterator and we would do a cache find, and we would do that std string from the string view. And of course, that would create a temporary copy. Whereas now we don't have to, and we can do a comparison with 0 allocation. And so the ISO 8583 has 128 potential fields in it, and the merchant ID is just one of the items that we look up. And so string view on this particular data structure that we get for credit card transactions is a huge win, and being able to use that with unordered map was just that much more. And so with zero allocation lookups on 540,000 merchant resolutions, it's not a huge win from the allocation. I mean, honestly, I say it's a huge win because to me, it's just easier and it's cleaner looking code. I mean, to turn around and do my cache find right there on the string view is just cleaner versus doing the std string. I had someone ask the question inside Discord, is it supported in std map 2? And it's supported on unordered set and unordered map. I don't believe it's supported in std map, but maybe someone else can answer that. I at least have never used it for std map. So to that point though, you can gain another 1.3 times speed up just by using heterogeneous lookups in C++20. So another thing I want to talk about, because we talk about how, different containers are useful for different things, and unordered map, iterator stability and when to use std map, because if we turn around and look at the snippet of code, if we end up taking a pointer to something that is inside of an unordered map, that's going to be a bad thing, because unordered map, if we end up doing a rehash, it's going to invalidate all of our pointers and all of our iterators. And so that is just going to lead to probably an undefined behavior mess. And so if you actually need that iterator stability, well, that is one thing that std map ends up giving you, right? Because an insertion never invalidates the existing references. So if that is a way that you use your code, that you're taking a pointer to the item, then you definitely want to probably stick with std map. All right, so our decision framework, how to choose the right container. So std vector is your default sequence. If you're writing something and just coding something up and you just need space, well, go to std vector. You're set to go. If you're doing a key value, go to std unordered map as your default associative. It is, as the line says, O(n) fast, but O(n) dangerous. But we covered what those dangers are, right? So if you know that you're creating a good hash, then you're going to be able to help avoid collisions. And if you start to understand what your data set is, then that you can automatically do your sizing so that you don't have to worry about going through and doing the rehashes. So bad hashes, make sure to use hash combine as we shown in the code there. That's a pretty easy copy and paste, C++17, easy pattern to use. So collision, hash all your fields. Don't just do US dollars. Or, you know what I'm saying? Make sure that the data that you're using, make sure what the values going in are. Make sure that you have some uniqueness in the data fields. And rehashing, just call reserve, and for us, there were definitely times that when we first started processing transactions, we would see our queues fill up because, if you're processing transactions between 8 and 9 at night at any part in the world, well, there's a lot of people, or not even 8 and 9. If you're going from 7 to 10, people are out for dinner, people are out at with friends, and so your transactions speed are much higher than say at 2 or 3 a.m. And so we definitely found that we had to adjust our code so that we learned from what was going on, and we made sure to call reserve to keep our performance gains consistent. So your new decision tree, do you need to store items? Okay, if it's a sequence, you just use std vector, almost always vector, you're done. That's the way to go. If it's a key value, if it has to be sorted, okay, if you need this data sorted to start with, go with std map. But then also keep in mind, std map, you're not going to get the speed, but of course, as we talked about, if you need reference stability, well, std map is definitely going to give you that. Otherwise, start with unordered map unless you know for a fact that you need any of the others. So I like to break it down. Sequence, std vector. Otherwise, unordered map until I'm proven otherwise. And if you know the size, well, custom key, make sure if you're using unordered map, use hash combine or just write a good hash function and know the size, call reserve. So stop using std map just in case. Start with std unordered map. If it's not vector, it should be std unordered map. You know what the pitfalls are, and now you can just write, more modern and faster C++. And so I want to say, Pack Publishing, like when I do talks and you come see me in person, I'm normally giving out books when you find mistakes in slides. And we might revisit that as we go on and I take questions. But if you go to Pact, that coupon CPP Online, I believe it gets you 20% off of any of their paperback books or any of their digitals. The QR code there is a link to the GitHub where all of these slides are. It's reveal.js, and so you can get the whole talk as well as all the source code. The source code was built on a Mac. It's got all the CMakes. It has the VS Code, so you really should just be able to open it up and play with it. You can find me on LinkedIn if you want to connect, and otherwise I look forward to taking questions, and I really appreciate you all spending the time with me for the talk. Thank you.